Hello.
Hey.
Hey, hi Fabian.
Hi.
All right, it's about time. Just before we start, a reminder for the seminar students to please turn on their video and use their full name so we can track the attendance. And with that, I'm very happy to welcome Fabian Beck and Shivam Agarwal to our lab talk today. Unfortunately, the German railway has hijacked our plans a little bit. So it's an online-only talk now. And just to introduce Professor Beck, he's a professor at the University of Bamberg and is chair for the Information Visualization Group FAIR. He's working on visualizations with respect to dynamic structures, and he applied this kind of visualizations in many areas like software visualization, which will also be part of the talk today, and other aspects like organizing literature. Before that, he was at the University in Duisburg-Essen. He received a couple of awards, among them the EuroVis Young Researcher Award, and he was also appointed a junior fellow of the EUROGRAPHICS and Association. And the talk will be given together with Shivam Agarwal, who is a research associate at his group. And he's currently a PhD candidate focusing on various aspects like data visualization in connection with artificial intelligence and visual analytics, also within the game domains. So we have published a couple of papers together, and so I'm very happy to welcome them today, and the floor is yours.
Thank you. Thanks a lot for the invitation, and it's really a pity that we can't be there with you in Linz. We should do that another time. Yeah, this talk is about understanding complex behavior from dynamic graph visualization to visual game analytics. So I would like to start with observation that our world consists of various dynamic processes that we only partly understand. And yeah, often that's quite okay. I mean, we don't need to fully understand the physics to use a bottle and drink water from a bottle. But in terms of professional applications, we often need to go a level deeper. When designing a bottle, it's a totally different story. We should really understand what's going on and to design a good bottle and one that is closing perfectly and so on, so that no water drips out, stuff like this. And a bottle is still a very quite simple thing. But here we want to look at more complex dynamic processes where we have different agents and objects that somehow interact with each other. It could be humans that are involved. It could be passive objects like a bottle, but also more complex machinery like computer systems or any kind of other machine, or nowadays also AI systems. So these could be the agents and objects. And then we want to study the temporal development, the dynamic process that these objects and agents are involved in. So we're talking about temporal data, and often events play a very central role to that. They are the discrete things that change something in this process. But there can be also continuous developments that can be described as time series, for instance. And then we want to study specifically the relations between the the agents and objects connected by these events and temporal developments. So we can model this as graphs and networks and visualize them also as such. And finally, the context is in many application areas very relevant. It could be spatial context, so where the bottle or something is located in the room, but it could be also non-spatial aspects. So what is the concept of a bottle, for instance, so semantic aspects, but also other aspects of data that are non-spatial, but need to be understood to really follow what's going on. So we've studied such complex behavior through visualization solutions, and we'll present some of our work here in this talk. And to connect the works a bit and to give you kind of an overall story, we want to cover always three different aspects. First, the dynamic interactions. So the dynamic relations that form between the agents and objects, or sometimes it's only just there indirectly, and we can speculate whether there is a connection or not. Then an application-specific embedding of these dynamic interactions into spatial and non-spatial context. And finally, comparison. Not a comparison across time, that's taken for granted because we want to study, of course, the temporal development, but an additional comparison that relates to comparing different variants of a process. So it might be executed by different people or in different contexts, and we would, through that, would get different variants of a comparable process, and this helps to understand the outliers, for instance, or the regular patterns that we see across these different variants. And since we will do these kinds of analysis with timeline-based visualizations, mainly it comes quite natural to give you also an overview of this talk on a timeline and give you a bit the background of the story, how the whole thing developed in my group and my personal research also. It actually goes back to my very first paper that I published still as a student, as a master student in 2008, Timeline Trees, and progresses basically through my whole academic career so far, namely the dynamic relations, and I will show you different approaches from that domain. That will be the first chapter, and then the second chapter is a bit newer, where the focus is more on the visual comparison of different sessions. And finally, so this is kind of more, it will cover different application areas. You will see that, for instance, software engineering, but also other like sports analytics. But one application area where we want to go a bit deeper, and Shivam has investigated this area, is game analytics, and that's also where we collaborated together with Günther, and we will show you two approaches in slightly more detail in this section. So generally, you will see a lot of different visualizations, a lot of different timeline-based approaches. I won't have the time to go in detail for every of those. If you have any questions about this, we can later discuss that in the Q&A. And we provide always the links to the papers, and when available also the tools on the slides, and I think they should be referenced in the YouTube channel, or we can also post the link to the PDF of the slides here in the chat. Yeah, so let's start with the dynamic relations. So yeah, sorry to mention that's kind of the subtitle of the talk, from dynamic graph visualization to visual game analytics, the story we took over the past 15 years already. Yeah, so let's jump in and discuss the dynamic relations. And the first visualization approach that I was involved in, it's called Timeline Trees. Before we go into the details of this thing on the left, bigger data set, we can first look to the smaller data set on the right, which shows an analysis of imaginary shopping carts. So you have different types of products, and one column here is basically one shopping cart ordered by time, so time from left to right. You see how different customers would buy different products, which ones together, and how this changes over time. So maybe things bought in the evening are different than those in the morning and so on. So you can analyze the shopping behavior through this, and this is a very simple tool with only data set with only a few different kinds of products. The height and color identifies the quantity, and then you see these small thumbnails, which actually indicate a bit more the interactions between the different types of products. Every of these thumbnails is basically a small version of the whole timeline here, but just highlighting those products that are bought together with the one in focus, which is for the first thumbnail, the cheese products. So you see to which other products the cheese relates, or which are often bought together. And then we have a bit of embedding here, an interactive hierarchy, and I can play a video. I'm still a bit proud of the interactions that I implemented back then, when it was a bit more difficult than nowadays to have these. So you have tooltips, that's pretty standard, but you will see in a second also that you can interactively collapse and expand the hierarchy to have different views on the data set on different levels of aggregation and abstraction. Maybe while the video is still playing, we can switch also to the view on the right, which is an left, which is an example from sports analytics, a soccer match from the World Cup in 1990, Germany versus Netherlands, there we can see who was playing together with whom. Of course, people play together within their own team. So whenever the ball possession changes, this causes a new transactions, what we call it here, a new column. So we see how the team interacted within the teams. There are only very few interactions across teams. For instance, one where Rudi Völler and Frank Rijkaard are involved, who got into some kind of dispute or fight, and then both received the red card and were sent off the field. So you will observe stuff like this, but you can also see the different roles of different players within a team connecting to different parts of the midfield, offense, and so on. And considering this approach in the light of our 3 dimensions, this quite nicely already shows the dynamic interactions, although through the thumbnails it's maybe not perfect, and you just get a rough feeling, and maybe it's hard to read the individual connections, but you will be able to see some of these interactions between the different players, for instance. The embedding, there's no spatial embedding. You don't see the soccer field or something, or the layout of a supermarket or so. But at least through the hierarchy, we can still preserve parts of that. So, for instance, dividing the players into defense, midfield, offense, and of course, goalkeeper. And there's no comparison yet here in this approach. This has been the starting point of a line of follow-up works on dynamic graphs. So maybe briefly, let me introduce the concept of a dynamic graph, which is basically you take a graph or network, a static version, and add a time component to it, and then you get different snapshots of the same graph. So the same nodes usually just connected differently across time. So if you look carefully, you see some differences between these juxtaposed diagrams. It's a straightforward visualization already of this, just juxtapose different versions of the graph, but you can already imagine that, yeah, this doesn't really scale well, and already with this small toy example, it's hard to see the differences really between the different versions. There has been a lot of research on this field of dynamic graph visualization, and we contributed to that, and also wrote to state-of-the-art report on the field. First version in 2014, and then a second updated version in 2017, and developed this taxonomy here to structure the whole field into animation-based approaches here on the left mainly, and timeline-based approaches. And our contributions were almost exclusively in this timeline-based area, mostly node link diagrams, juxtaposed ones, a bit like this one here, but you will see the difference on the next slides, how we could make such a thing more scalable. And the other one is a layered matrix-based approach that I will show. Okay, so yeah, one quite successful one, also quite well-cited one, is parallel F-splatting, where we use the timeline similar to in timeline trees from left to right with like small columns, but now it's not just the transaction that shows in each column, but a whole graph version. So before we look at the big picture again, I can show you this in a smaller example to help you understand what we are doing here. And so this would be a regular node link diagram of a weighted directed graph here with the colors encoding the weight of the edges plus a hierarchy that we use for structuring the nodes a bit, very much like in timeline trees already. And then we shift this layout from a 2D layout to a 1D layout, basically arranging the nodes in one line. But in an earlier version, we tested also like using arcs then to connect the nodes, but this doesn't scale very well. So we decided to split each node into 2 nodes and arrange all edges from left to right. So here, all edges you can just follow from left to right. And we aligned also the hierarchy with the linearized layout. So they basically match node A, node B, C, and so on. And this layout we can now use for what you see on the left-hand side. We can condense it in these columns. So what we do is we don't show these little arrowheads. They are redundant because we know that all edges go from left to right. And we don't need to show the nodes really as circles, but we could just have them very condensed on this linear axis here, the parallel axis. And then we can add multiple versions of that, like in timeline trees as columns, showing the whole thing on a timeline. And for the hierarchy, we also switched to a bit more scalable version, an icicle plot instead of this indented layout here. And so that's the thing you see then on the left-hand side. This is showing an example from software engineering where we showed the dependencies of JUnit, a software system, across many versions, like 20 versions. And you see how the dependencies change across these versions when there are bigger changes like here or here in version 4.0. And in this overview, you already see various different interesting things marked here with the different labels, but sometimes you also need to switch to a mode where you better see the added and removed edges, and then you could figure out some details and see also some smaller changes. One thing I forgot to mention is we don't plot here the edges directly, but kind of compute the edge density in these columns, and this gives us a better structure in these very dense areas where we have a lot of edge crossings. And we could still preserve this structure here. That's the edge, oh, there's a typo, edge splatting part. So plotting the density. Great. Yeah, with this, we even more better show the dynamic interactions. You can actually read the edges and get a richer picture about the interactions over time. We again have a bit of contextual embedding through the hierarchy, but not a lot. And again, no comparison yet. The next thing introduces a bit of comparison, but first it's basically showing the same data as before, just in a quite different representation, which is an adjacency matrix here. So again, we have the JUnit system and the dependencies within the JUnit system, but now as an adjacency matrix where the roles and the columns are the nodes, so the elements of the software system, and the dependencies between them are now these colored marks in the matrix. And we have again an icicle plot to group them, and then we see some clusters here. So typically along the diagonal of such a matrix, there are more dependencies than off the diagonal. So with this, you can also nicely study kind of the architecture of the system and see different layers of the system. So this part here has a maybe different role than the other ones. And this we can do in multiple versions and then connect the different hierarchies here. So here, really, the hierarchy can also change. Previously, the hierarchy was static or kind of a superset of all the available hierarchies that we observed across all versions. But here we can change it really in one together with the dynamic graph. So here we have the dynamic hierarchies and the dynamic graphs together. And better see the structural changes in the hierarchy also, that there's a package here that got expanded with more elements, and then here there was some restructuring and also deletion or maybe renaming of things that could not be tracked then, and so on and so forth. And now the element of comparison that we introduced here is we are able to show an alternative version of this. It's not an alternative version of the graph. We didn't go so far here, but just an alternative version of the hierarchy, which is basically, and which is still showing the same graph information, but just because the nodes are then here reordered, it looks a bit different. So it's basically the same graph, but in a different order if you compare the two versions here. But because the hierarchy is different, and you can observe here in this row between the rows, basically, the changes between the hierarchy above and the hierarchy below. So what we did here specifically is we used the original package structure, how this developed over time in the lower row, and in the upper row, we used a clustering algorithm, a dynamic clustering algorithm that produced a hierarchy for every snapshot of the graph automatically, and maybe can reflect a better grouping of the elements of the software system. So you can study here the differences to see whether maybe the algorithm suggests some improvements to the package structure, the organization of the software system. So again, this quite clearly shows the dynamic interactions. It has, through the hierarchy, it has a bit of embedding, and now it has also already, through comparing the hierarchies, a bit of comparison, but not as much as we could have, which is part of the next chapter and the next example. So this is a nice bridge to our approaches that focus more on visual comparison. The first approach that I want to show is not so much showing complex dynamic behavior. It's showing trajectories of people. We had the use case of extracting trajectories from Twitter data. So people have publicly posting geolocated tweets. You can aggregate those or estimate when they move to a different place, so traveled to another place. So for instance, if this was a long distance and short time, then we could guess that this flight was a flight. And extracting this information and aggregating this for kind of a large group of Twitter users, we got some overall worldwide pattern, or here in this case, US, and could estimate some flight data from Twitter. And we want to see if this relates to the kind of ground truth that is available for flight data. So we took some other data set where actually the actual flights that happened were taken, and we wanted to know whether this is the same or different. So you could just juxtapose these two views. You'd have the connections here in a grid structure. So it's basically a map of the US subdivided into a regular grid structure, and then connecting the regions where people kind of, we estimated, or in the flight data set where we had data that there were flights, and for Twitter where we estimated that. So you could put these side by side and see already that there are some commonalities on the east and west coast, but also some differences. So this might be Atlanta, the airport, or this, I'm not sure. But here there's a slight difference, but it's not super clear. So we might need something better, maybe something like a diff version of this network, and we did exactly this. We merged that into one graph network structure, and then are just highlighting the differences between the two. This is for a different region, but basically the same data, comparing flight data to Twitter trajectories. We observe here some clear differences in China, where the flight data is more pronounced, and in Japan and Indonesia, where the Twitter data is more pronounced. And this can be easily explained by the popularity of Twitter in these countries. As it's not very commonly used in China, we don't have a good coverage here. This was a bit an expected effect, but it's nicely shows up in the visualization. And we have this as a graph view or heat map, but of course, in the context of this talk, this graph view is more important. But still, it's kind of not really showing the complex behavior in the sense of temporal resolution. We just aggregate across time into one network. So this is not so pronounced here. On the other hand, the spatial embedding is really preserved here. We just use the map, the original embedding, and we focus on the comparison, although not really looking into the comparison with respect to time. So whether really we just observe if the same quantities are there across time, aggregating the whole time span, and not see if maybe some of the flight data in the mornings or so is better, it can be better reconstructed from the Twitter data than the ones in the evening where people are too tired to post any messages or so. That's still missing here. Next, I want to present an approach where we go deeper into this comparison and preserve more of this temporal aspect. Another application area, here it's eye tracking. So people looking at some user interface or a stimulus, a static stimulus, we aggregate the eye movements into a graph representation where the nodes are areas of interest. So here, this example is, you can imagine a picture of a fruit salad where there are different fruits in the picture, and people are looking between apples, bananas, grapes, strawberries, and so on. These are the areas of interest, but it could be also an interactive user interface where people would look at different areas of the user interface. And now the question is, okay, we get per user one of these graphs. We visualize them here as these radial graphs. The colors indicate the different areas of interest. The size of the ring segments is the length of fixation. And then you see the connections between these areas of interest. But now the question is, how does the viewing behavior of Jane compare to John? Is it the same or not? So you can put them side by side, but it's hard to see the differences. So we developed some comparative visualizations for that, where we show in a matrix all possible comparisons, and then could see which ones are more similar. That's the ones with a gray background, and the ones with a lighter background are less similar. And then we can click on one that is of interest, and then we see that in the detail. Similar to shown before, we encode in blue and red the different weights of the edges, and gray if it's the same. And here, I forgot to mention this, there's also a time slider, so we can see the sequence of the areas of interest that people look at across time, and can compare also these sequences here and see that it's quite different patterns still in this case. So this approach is showing the dynamic interactions wide clearly. It still aggregates to some extent, Then we have this interactive slider, but maybe not perfectly. It has a little bit of embedding, which would be here the stimulus as an image or video, which is for copyright reasons not contained in this figure. And the focus is really here the comparison. There we have really different views, and we can do an end-to-end comparison, but also a one-to-one comparison. And that was the focus of this approach here. I have another one, but probably in the interest of time, I will skip this. And you can try out the tool yourself or look at the paper that is linked here, which is a bit more generalizable, but also a bit harder to understand maybe. So let's skip this, and I will hand over to Shivam now, who will be talking about game analytics.
Well, thank you, Fabian. So in this chapter, we'll see two examples from game analytics, how we can understand the complex processes. Okay, let's begin with the first one. I'm sure you must have heard or played or seen the game of Bomberman, where the objective was to lay bombs to kill your enemies and complete the game levels. This is a simulation by AI community of the same game, but here specifically, they wanted to investigate the complex behavior of agents that goes on with cooperating and collaborating with other agents. Hence, in this simulation, what they did was they made two agents in a team competing against another team. So naturally, to build a strong team, they have to compete against another team and also collaborate within their teammates. The grid of this environment is basically 11 cross 11 tiles. The tiles are one of the three types: a navigable space, a rigid wall that can be broken by a bomb, and a rigid wall that is unbreakable, and a wooden wall that can be bombed. And as you guessed, each agent can do nothing in a time step, move in one of the four directions, or drop a bomb. Once a drop is dropped, it explodes after 10 time steps. This weight of 10 time steps was critical so as to train the AI agent, or it mandates the agent to learn the phenomena of explosion and plan accordingly. Once a bomb explodes, the flames persist for 3 time steps. And if during these 3 time steps, any agent comes in these tiles, in the vicinity of these flames, they die. Okay, this was the action space and the rules of the environment. But to help the agents conquer the game, they also have some power-ups hidden behind the breakable walls. First is the extra bomb. As you guys guessed, it allows the agent to gain an ability to drop one extra bomb simultaneously. So by default, they can only drop one bomb and have to wait until that bomb has exploded. Again, this is a constraint not to encourage agents who only drop bombs randomly in an unplanned manner. Second power-up is allowing the range of the bombs to be increased by 1 tile. And these 2 power-ups can be gained many number of times, which will increase their capacity of doing these 2 activities. A third binary power-up is the ability to kick a bomb. And as you can guess, if an agent kicks a bomb, the bomb kind of goes away until it is stopped by another wall or another agent in the direction of movement. And again, this is, if you remember Bomberman, if you have played it yourself, there was also this ability. And it's really a nice ability because you can plan your moves in a sequence and time them correctly to have a really deadly move. Kick a bomb before it explodes, and it explodes near your enemy. Okay, so with all this, what the aim of AI developers is to train them to be a better agent and kill their enemies. And let's watch a battle playback of how these developers understand the qualitative behavior of their trained agents. And you see, okay, it's very fast. There are some power-ups now. You are seeing the range of bombs increasing. The red agent is quite fast here. Still, all 4 agents are there. That's a long range bomb now. Oh, that's a long bomb chain. And one agent, red agent is really quick, and one agent is already dead. And the blue agent is being cornered now, and the red agent is successfully cornered and killed it. Now, this is the usual speed of playback which AI community used to understand, okay, whether they have learned to exhibit certain types of behaviors or not. But as you can imagine, watching this playback to infer whether agents compete or collaborate is really difficult. Hence, we designed a timeline to understand these complex processes. Here, for context, we said that, okay, 2 agents of first team should be visualized in the first 2 rows of this timeline. So here, in their respective timelines, we draw some events. For example, their movement with orange lines. Light blue color shows laying a bomb, picking a power up by green dot, kicking a bomb by pink circle, and so on. And the power-ups, which are kind of the common resources in the game, you can imagine these resources are something which the 2 teams have to compete with each other to get them. They are placed in the middle rows. Having said that, how we encode the bombs. The light blue color shows a laid bomb, but also below each of the timelines, you see this icon, which shows that a bomb was laid by a head, followed by a tail, and then a gray rectangle showing the blast or the explosion of that bomb. And then you can see, okay, that there are pink dots connected to some of these bombs, inferring that these bombs were kicked by the team, by the player. And here in the middle, you can see already that there are many vertical lines. So vertical lines encode interactions. Interactions could be with the power-up, which is picking up the power-up, or also kicking a bomb. Here, interestingly, in this example, you see that a bomb was kicked, the bomb moved, the bomb exploded, and then followed by a black or a gray circle indicating the death of a different player. So again, kind of effectively showing the maneuver of kicking a bomb and killing enemies. This timeline was part of the full interface as shown here. The other components in this interface on the top shows game statistics for different sessions. So the timeline shows the behavior of 2 teams for one particular game. And the summary component above shows it for many different games. On the top right is the same battle playback that you have seen. Kind of mapping this to the 3 dimensions, which Fabian showed before, we showed direct interactions with the power-ups, yes, but the indirect interactions, like how the actions of one agent affects other agents, that has not been directly shown here. So that's why it is kind of showing, it is allowing to infer the effect, but not showing the direct interactions. Regarding preserving the contextual embedding, so separating the 2 teams on the top and bottom rows, power-ups in the middle, preserves some context. But as you can imagine, in the timeline, there is no way to ensure, remember the situation where one agent was cornered. It is not visible easily in the timeline. You still have to kind of rely on the playback to get exactly that situation. And comparison here is, yes, you can argue that it is between 2 teams competing against each other, but then there is no comparison of 2 sessions, 2 or more sessions. With that, there is another environment which we worked on, which has many more agents. So there is no upper limit on the number of agents here. This is a flatland environment. And the objective here is to schedule each agent, which is a train on this virtual rail network, to go from their source station to destination station. And here the trains can move forward on this fixed track. All the trains travel at same speed. The catch is that here they can experience random malfunctions. So they have to stop when the malfunctions occur. And when they come head to head, there is no way to go back. Hence the trains get involved in a deadlock. this is a much bigger environment with many number of agents, but still there is no, the main emphasis is on collaborative aspects. And as you can get imagine here also, relying on playbacks is a usual thing. So here you see several trains moving around in the fixed track, and some trains disappear when they reach their destination station, but you can see how crowded it becomes and how fast it is. But the similar question arises that how to compare the behavior of AI teams. For this, we focus specifically on the comparison part, and this was a full interface which we developed. On the left, there is this timeline, which shows the comparison between two AI teams. And on the right, we kind of try to preserve a bit more spatial context. So I'll talk about the spatial context in the remaining time and not on the timeline view. So I'll skip this part. Yeah. Okay, so to look at the spatial aspect, what you can do on this map of virtual real network, you can specify a region, for example, by drawing a rectangle like R1 here. When you draw a rectangle or a specified region, it becomes a node in a graph. And the size of the node captures how many trains went through this region. The arrow shows the movement of trains between which regions. So this is kind of an aggregated graph, aggregated, directed, and weighted graph. The width of each edge also shows the number of trains that move between the two regions. How we can draw this in the comparison aspect. So you'll see some colored pies inside the node on the comparing of two episodes. So we select a region, there is a node now. The blue color shows one AI team, the orange the other team. And as the regions are selected, you see this graph growing. And the kind of encoding with two colors shows how many trains visited each region and the transitions between the two regions. Hence, the spatial aspect is a bit more here, and the comparison aspect is more integrated in this visualization. Hence, we assign 2 stars for this. Next, then I give it to Fabian.
Thanks, Shivam. And yeah, so you saw on the last slide, previous slide, that we haven't fully managed to fill all stars in one of these approaches. So we had different focus, but maybe the last one was the most balanced one in terms of balancing these 3 dimensions. But obviously, there's still some stuff to discuss. So first of all, the usage of timeline-based visualizations that we've seen. We are still quite happy with this design decision, but it comes with a big challenge. So we are spending already 1 dimension for the time, which just leaves us with 1 dimension for the rest. You could argue about space-time cubes, 3-dimensional space-time cubes. That's maybe an option. We haven't explored that really. Another alternative would be to use more animation. So instead of showing everything on a timeline, you just show 1 state at a time and then do that in an animation. But there, we didn't use that because in most of the cases, because of it gets really hard to get an overview of the time. And if you want to go towards comparison of multiple sessions, it even gets harder because you might want to compare something from the beginning of the first session to something of the end of the second session, and that would never show at the same time. So the whole alignment gets even more problematic. But still, it might be interesting to explore those hybrid approaches for dynamic graph visualization. Other researchers have started to investigate that direction already, and that could be also promising for instance, game analytics, to look at combinations of animations and timeline. Application-wise, we have really covered a diverse set, but they have in common that these are all non-trivial systems that somehow exhibit some complex behavior. And these can be found among technical systems, software systems, AI systems, robots, or human behavior, of course, work processes, sports. We saw an example for this. but you could also study social networks, of course. And then the combination of the two, which is maybe the most interesting one, human-machine interaction. So any sorts of humans interacting with user interfaces, for instance, studying this through eye tracking. But next step would be also to move from just AI-based system to human AI interaction or human robot interaction. That would be pretty interesting use cases. In all of these, they have kind of in common. So as I said, initially, we look at professional applications of this. So what we've presented are expert tools. So I hope we could give you some insights on how they work, but the expectation is not that you can understand each of the visualization, all details in 2-3 minutes, but maybe it requires a bit more of training. But the general task is always the same, to check whether the system or the process behaves as expected or can be optimized somehow. That's the goal of understanding this complex behavior. There are some open challenges that we see. One relates to the embedding of spatial and non-spatial context into timelines, which is very difficult because just showing the events on the timeline usually consumes all the space. But it's, for instance, in the case of Bomberlytics, Bomberman, it would be really important to see also in the timelines these cornering situations and so on, to preserve some of the spatial information somewhere in the timeline. We don't have a clear solution for that, just the idea that this is still somehow missing. And then the comparison, so often it's doable to do a one-to-one comparison, something like a diff mode. We've seen an example of this. We've also looked at examples for more than 2 sessions, but this gets a lot more complicated, and also our solutions do not feel so complete yet in this regard, and there would be more effort needed, I think, to better study these scenarios where you need to compare many more than 2 sessions with each other. And then finally, multi-level and adaptive abstractions. We've seen a little bit of this in Flatland, for instance, where you do the adaptive abstractions through marking those regions of interest and then building the graph structure, but also a bit of multi-level abstractions in those first approaches, timeline trees, where you can use the hierarchy to collapse part and can study multiple levels of abstractions by collapsing parts of the data. With this, I want to conclude our journey from visualizing dynamic relations as graph structures to visual comparisons of these things. And yeah, Shivam presented nicely this application examples from game analytics that have really complex dynamic behavior. Thank you.
Thank you very much for the very interesting talk. With that, we have still a couple of minutes left for questions. So feel free to go ahead, ask your questions, or put them in the chat.
So I would already have a question. Can you hear me well enough?
Yep.
Okay. So you presented, for instance, these 2 visualizations for these 2 environments, the Bomberman and the train game. And I was wondering whether you sort of tried to categorize what aspects of these environments make it possible to apply the specific visualization that you applied to them, and what other popular environments there are out there that have the same attributes that would make it possible to use the same type of visualizations on them.
Yeah, that's a great question. Thanks, Christian, for that. So definitely, when designing the visualization, we had to keep the context in mind. So, for example, in Bomberlytics, there are definitely 2 different teams. So to investigate, to enable investigation, the interactions between them, between the teammates versus the other team, we separated them into top and bottom rows, and the power-ups were in the middle. But this was in the context of Bomberlytics game. But if you can imagine any other environment which has similar setup like 2 teams, this design could still work. But if the team size becomes a lot more, for example, 10 agents versus another team of 10 agents, then it becomes already crowded. Among other environments, there are still many more challenges. For example, there are many large environments like neural MMO, where there are thousands of agents, and the goal is to build multi-agent reinforcement learning agents, which kind of learn the cooperative and competitive behaviors on scale. So there, I just gave one example, but there are many more such environments being proposed in the AI community.
Yeah,
Thank you.
Also comment on this. It's a general question also for us. How can we, this line of research, can we kind of condense this into somehow a framework or library or so, where you can have different building blocks? So maybe if you compare timeline trees to analytics, you still see some similarity. One is maybe sport games, soccer, and the other one is it's also two teams playing against each other. And we have a couple of more examples, and they also visually they sometimes look quite close, and now could be also an open challenge how to build a framework around this to say, okay, in this case you have two teams, you can do that, and we have these building blocks ready, and you can just construct quickly a new visualization.
Okay. Yeah, thank you, and thank you for the great talk.
Any further questions? Feel free to just unmute yourself.
I would have a very quick one. First, thank you both for the talk. In the beginning, you mentioned that you focused mostly in your research on the superimposed, if I understood correctly, on the superimposed technique. Why have you invested more in this technique in comparison with the other ones so far? And yeah, thank you for the talk once again.
By chance, I picked the right slide. So the superimposed here. No, maybe that was too quick. What we showed is the juxtaposed layout. So maybe to so in visual comparison, there are basically three approaches. One is to put stuff next to each other. That's juxtaposition. You have then this idea of overlay or superimposition, and then the idea of kind of a diff mode, an integrated or explicit encoding, it's sometimes called version, and that's here reflected in these three categories. So what we've shown mostly are juxtaposed things, but not just like here, putting them just somehow next to each other, but somehow aligned. So we carefully designed that this is easy to read, to see. So you usually can follow a straight line to see what happens to an object over time. And that is very important, was very important for us to make these juxtaposed representations more effective. Do you recall any superimposed ones? Or I mean, the diff modes are kind of an integrated representation, if you like. Yeah. But this is a bit different than here in this taxonomy. Here, integrated would mean to kind of not have a timeline, but somehow maybe have a curved timeline through some network structure. So integrate the temporal differences somehow with something else. But here, the idea of comparing sessions is not reflected here in this taxonomy. Mm-hmm. Yeah. Yeah. Does that clarify? And why we chose that, maybe that was also part of the question. We had the impression that the juxtaposed ones scale quite nicely to at least like 20 time steps of a graph, or those typical length of the games, while superimposed would probably just work with fewer instances over time. Still quite similar to an animation where you could have only a limited time frame that you see at once. So in animation, typically just one state, and superimposed would maybe look a bit into the future and backwards, but cannot show larger differences across like larger time spans.
Right, any further questions?
One comment that comes to my mind is also on the superimposed one. I mentioned space-time cubes, and that would be exactly a superimposed one, where you take the base layout as a 2D layout and then stack the versions over time on top of that, and then you get a 3D model. And then the question is what you do with this. You can just handle it as a 3D model, but you can also use that just for navigation and then have a 2D view, and you can cut somehow differently through that 3D model and then get different representations. Yeah.
Would you also say the motive would be easier explainability to people who are not familiar with the field of visualization in general, or you wouldn't say so?
Node link?
Sorry?
Which version should be more intuitive to understand?
The juxtaposed, maybe? I mean, superimposed would not be, if it was an animation, maybe it would be more easier to understand, I would say, just at the top of my mind, right?
Both is not difficult to understand and comes quite natural, but maybe animations are sometimes even easier to understand than timelines. But also people are used to this timeline representation just from history books also. So here the focus was not to come up with the most intuitive representation that everybody can quickly understand, but of course that could be an interesting direction to now move to application areas where it's a broader audience. We do a lot in this regard also. What we haven't talked about this line of research on data-driven storytelling, but that would be interesting to integrate our line of research on data-driven storytelling with this complex dynamic behavior. And then we should think a lot about these questions and maybe would opt more for animated approaches, because sometimes they are a little bit easier to understand and not as overwhelming as some of our timeline-based representations.
Well, just to add a bit of the explainable approaches, so there are different ways in which we can make more intuitive, make the representations more explainable. We experimented with dynamic natural language text and visualization. We submitted that as a poster in EuroVis last year, which was understanding the evolving behavior of AI agent being trained in Power manner. So we did some preliminary work, but yeah, there's the line of direction which we still would be experimenting on.
All right, thank you very much. We are almost out of time, as I see. So thanks again for the great talk. And yeah, hopefully we can manage to arrange something another time as well, when the German railway is not striking. All right, thank you very much.
Thanks for the invitation.
Next talk will be on June 14, and it will be given by Olga Avanasieva from Good AI. So feel free to also join in that one. Thank you. Bye-bye.
Bye.